In this video, we're going to talk about when to use the expected value to calculate an average and when to use the sample mean to calculate an average. The expected value of a discrete random variable is specified by the individual values of that random variable x1, x2, all the way down to xk, and then the associated probabilities. The probability that the capital X, the random variable, is equal to x1, and the probability that capital X, the random variable, is equal to the value x2, and so on all the way down to the kth value. The expected value formula is then given by this expression. On the other hand, if we have a sample from the distribution of x, then we have data y1, y2, all the way down to, let's say, the nth value, yn. And then if we have data such as that, we could simply calculate the sample average. Suppose that a fair 6-sided die is rolled 5 times, and the results of the rolls are shown in the pictures below. So the first roll was a 3, the second roll was a 6, etc. Well, the sample mean is simply calculated by taking the values of the rolls, 3 plus 6 plus 5 plus 5 plus 4, and dividing by the number of observations, which is 5 in this case, and calculating the result, which is 4.6. The values that we obtained, 3, 6, 5, 5, and 4, is a sample from the probability distribution of x, where x is equal to the value of the die. And that probability distribution of x is pictured in this probability mass function over here. Along the x-axis are the possible values of the die, 1 through 6, and on the y-axis are the probabilities, and they're all equal to 1 out of 6. Because each side of the die has equal probability. The expected value of x, or the expected value of that distribution of x, is equal to 3.5, and that can be pictured right here on the graph. So notice that the sample mean is 4.6, but the expected value of the distribution of x is equal to 3.5. And we wouldn't expect that the sample mean will always be the same as the expected value of the distribution where the sample comes from, because the sample is random and it's going to vary from sample to sample. But one thing we know is that if the sample size is large enough, that it will approach the expected value of x, and that's called the law of large numbers. In this plot, I've simulated rolling a die like this a different number of times. So for example, the first value here is I've rolled it once and I got a 5. The next value, I simulated it, I rolled it twice, and then the average value was 1. So it must have got 2 ones. And then the next time I rolled it 3 times, and the average was 3.3, etc. And this red line over here, you can see, corresponds to the expected value of the distribution, and we know that that's 3.5. Now I've done this where I've rolled it 100 times. Well, actually I didn't do it, but the computer did it for me. And you can see that as the number of rolls increases as it gets closer to 100, that the average gets closer and closer to 3.5, whereas earlier on the average there's some variability in the average where it's fluctuating around 3.5. So for example, in this one it's 5.125, and in this one it's 2.94. This is an illustration of the law of large numbers, and what it also illustrates is how the sample mean is related to the expected value.